process. Hopefully, when you have that write up, either today or latest tomorrow, I guess it will make some kind of a sense. So the idea is the controller part, which BD discussed, I guess that was quite straightforward. So whenever you do it, some have already done it, and whenever you do it, I guess that is manageable. But then all inputs were manual. I mean, the lower level sensor, the upper level sensor, everything was manual. And that is how you checked whether your controller is working fine. So the next part is, I've simplified what I discussed in the previous class. We just have to make a simple model of the upper tank. That will be a separate function block. And once you've tested that, it is just one simple integration function and two comparisons. I mean, it's much, much simpler than many of the assignments that you've done so far. So once you have that particular function block which represents the upper tank, you have your controller. That is what you do first. Second, you have your tank, a function block which represents your tank. And then, of course, the third part is you got to put the two things together. That means you connect your tank, you connect a controller to the tank, which in this case it is not a physical tank. It is a mathematical model, or it is a tank that is implemented in software within the same PLC which runs your controller program. So you hook up or you link your controller with the tank, and then you have a purely digital simulation of the entire system. The controller is, of course, always digital. It's always implemented in the PLC. But in this case, instead of having a real process, we are having a simulated process. That's part two. Okay, I'm not sure. Probably the last class was quite confusing. But then I guess once you have the write-up, it will be a lot more simpler. Today is the final part of the same assignment. It is just you're going to add this one, ornamentals. Because these days, whatever you sell, marketing is an important content of whatever you sell, no matter how good or how bad a product, how you present it is an important consideration. Possibly that is what we are going to do today. ওটাকে সাজানো হবে আমাদের সিস্টেমটাকে, and how do you do that? We develop a human machine interface, which in quotes is more commonly known as a visualization. The fact is, all practical systems, whether it's a process plant or whether it's machine control in a factory, their human machine interfaces are very extensively used. Ultimately, today, what you find is you have a few people sitting in a control room in the front of large screens. The entire factory, the entire process plant is represented there graphically. You can monitor the entire plant, what is happening where, sitting there in the front of this large screens, and you can control the entire plant sitting right in the front of the large screens. So that is the third part. Of course, not very new concepts. You've already done visualization with all the assignments so far. So this is nothing significantly different or dramatically new. But then I'm just going to show what we could possibly do in the context of your tank control system or level control system, whatever you call it. So I'll come to that. Here what you're seeing is a HMI screen or visualization, that as we call it in courses, that relates to the process part. You also have a visualization that is associated with your controller. Controller means the on-off controller that was developed as a part of version 1 of the assignment. There you had, or you will be making different kinds of switches. One switch will be for auto manual switchover. There in the manual mode, you'll have a start button, you'll have a stop button. Plus you had this one, alarm management. That is, example, if there's insufficient water in the lower tank, or probably say there's an overload condition, or probably say the upper tank does not fill up within a certain amount of time. All these are abnormal operating conditions. So whenever you have an abnormal operating conditions, you need to inform the operator. That is what an alarm is all about, informing operators about abnormal operating conditions so that they can take necessary corrective actions. But there, in the controller part, the entire alarm generation was your responsibility. You wrote the entire software, the entire logic for generating alarms. Fine. There, the number of alarms, I guess, was 2 or 3. Overload was one of the alarms. Insufficient water in the lower tank was a second alarm. And third alarm, I guess, was that your tank does not fill up with a certain amount of time. In a practical process plant, in a practical factory, the number of alarms could be easily in the range of hundreds to thousands. So if you have to write the logic for each alarm, if you have to write a dedicated logic for each alarm, so developing the program for the alarm itself becomes a huge task. So normally, alarm generation or the software for alarm generation the necessary software for alarm generation is built into this particular package, whether it's CodeSys or any other competing software for PLC programming. Alarm generation is built into this particular package. You don't need to write the software for generating alarms. You just have to configure it. For example, you've got to say the system that I want to generate an alarm if the some water level is low. Second, say I want to generate an alarm if the overload condition is true. I want to generate an alarm if the overhead tank does not fill up within this amount of time. So you just have got to state the conditions, the logic, the software necessary for generating the alarms is integrated, is built into CodeSys and all other similar software. Alarm management is a critical part of any such software. So that probably is a new thing that I'm going to discuss today. The rest of it is you've already done it before. So alarm management is how you define alarms and CodeSys. That's the only new thing. And I'll also be discussing this old thing. This is what is called a trace. Of course, you know what a trace is. But in any practical applications, you have what is called a trend. Trend and trace is very similar. There's just one small difference. Trend is a part of CodeSys as well. I mean, you have a trace, this one block. Besides the trace block, you have a trend block. But there are certain problems with trend in this particular CodeSys because it's normally meant for hardware PLCs. So if you try to use trend, certain errors are being generated. So that's why I'm using trace. But there's only one difference. I'll come to the difference. Now, why is a trace important in a process plant? Why is a trace important in a factory? I mean, this is nothing new. You already are aware of a few examples. For example, say you go to any commercial establishment these days, any shop, even a small shop or a mall or whatever, a bank or whatever, you have closed circuit televisions. You can find multiple cameras installed at important locations. And then you have one or more monitors which display the real-time feed. Real-time feed means whatever image the cameras are picking up, that is displayed on a monitor. So that's sitting in one location. You can have information about what's happening at each of the locations where a camera is installed. But what you see in the monitor is just the present data. I mean, whatever exists right at this particular point of time, that is what is displayed in the monitor. Now, if something abnormal happens, some theft or some accident or whatever, then what do? Or the main reason why you have a closed circuit television is now what happens is all the data that is collected from the cameras is actually stored within the hard disk. So this image feed is stored for a significant amount of time. For what amount of time it is stored depends upon the capacity of your hard disk and depends, of course, upon the number of cameras that you've got. But the fact is, whatever image feed that you have is stored in a hard disk. So in case of an abnormal situation, you can actually look back at what exactly happened at that particular point of time because you have stored this information within the hard disk. The second example that you're all aware of, whenever there's a plane crash, the first thing that people look for is something called a black box. It's not black in color, but still, what is a black box? Black box is again storage device. It's specially built that it can survive even if there's a plane crash. It can survive the impact of a plane crash. Even if the plane crashes into water, it can survive the submersion into water and all that. It's specially constructed, but it is basically a storage device. What does it store? All kinds of parameters within the aircraft, whether it's the engine, whether it's the flight computer, whatever. All kinds of important parameters in the aircraft, those data is stored within this particular storage device. And not only data, all kind of communication that takes place within the cockpit, that is also stored within this particular black box. So the event of a plane crash, people look for this particular black box, then they try to retrieve the data. The idea is to find out what exactly went wrong. Why did the plane crash? I mean, you have exactly a similar situation in a process plant or in a factory. Whenever there is some kind of a fault, some kind of an abnormal situation crops up, either in a process plant or in a factory, then possibly you want to find out what exactly went wrong. Why did this abnormal condition arise? So what is done is all important variables, all important parameters are stored again within a computer hard disk. There's a special server for that. It's called a trend server, but it's nothing more than a computer with a huge amount of storage capacity, which stores all information, all important variables within this particular hard disk. Whenever you have a failure, then what you can do is you can go back in time. You can look into the data that has been stored, just the way you look at the data that is stored in a CCTV system, just the way you look at the data that is stored in your black box. Here again, you can look at the data that is stored, historical data. It's called historical data. Why? Because it represents whatever that has happened in previous instant of time. So you can have a look at this historical data, and then you can find out what exactly went wrong, which variable actually led to the malfunction of this particular system. So that is why it is so very important that whenever you have a malfunction and you're trying to diagnose that particular malfunction, you're trying to find out what exactly went wrong, then this historical trend is extremely important. That is why any such system has a historical trend feature. Now, that is what we're trying to develop here. We're trying to, instead of a trend, as I said, the trend is not working here because we have a simulated PLC rather than a hardware PLC. We're trying to do the job with a trace function. The basic difference between trace and trend, you will have both in courses. Trace is, for example, in trace, when you define the time axis, you've already done this, you can define the duration. Say, default value is 10 seconds. It could be 10 seconds. It could be any other time. So you have the current value and you have the value for the last 10 seconds. The duration defined was 10 seconds. Or if it's 1 minute, you have the data, the current data and the data for the last 1 minute, 10 minutes or 10 seconds, whatever you've defined. Okay. In case of a trend, what happens is you can store data for any amount of time. The data is logged. Of course, it depends upon the capacity of your hard disk. But then you can store data for one shift, 8 hours. You can store data for 1 day. You can store data for even 1 month. provided you have the necessary storage capacity. So whenever something goes wrong, you can then look back into the historical data on this particular graph. You can just set the time. Say, I want the data from this date, this time to this date, this time. So what it does is calls back the data from that storage device, from the server, and then displays it on the graph so you can see what exactly happened at that particular point of time and what actually led to the malfunction or whatever problems you have. So the basic difference between trace and trend is the amount of time for which you can store the data. Trace is just current time to a little amount of history, 10 seconds, 1 minute or whatever. And trend is very long duration history, could be even in the range of months, provided the necessary storage capacity is present in your server. Okay, fine. So here, of course, what I'm doing is I've just tried to plot one variable. This is the level of water in the overhead tank. In our system, what we plot, you could possibly plot all important variables: level of water in the overhead tank, level of water in the underground tank, probably the overload condition of the pump, and probably whether the tank fills in the right amount of time. These are the important variables. So you could plot all of this. But in this case, I've just plotted the level data. Actually, I've not even plotted the level data. I've just kept a manual slider here. If you see this particular slider, this slider is just generating this level data. I'm not actually using any level system here because the idea is to show how this particular trace works. So let's run this particular system. Now this is representing, say, the level of water in the overhead tank. Now you can define what is abnormal level. Abnormal level could either mean that a tank is nearly full, or abnormal level could also mean that the tank is nearly empty. In my case, of course, that's your choice. The process engineer would define that what is high level and what is low level. In this case, just as a way of an example, I'll define that 80% and above is abnormal, 20% and below is abnormal. So anything between 20 to 80% is normal level. So normally, when the process is operating, the tank level would be within this particular band of 20 to 80%. You don't expect the level to be above 80 or below 20. If that happens, there's something wrong in the process. You need to troubleshoot that. You need to diagnose that and set it right. So let's increase this particular level. Now it's presently 51. If you can see it on the left, this is the level that's being manually set. I'll take it now. See, once it's 80, you've programmed this particular trace to change color. So this is what is new. You have used trace in quite a few of our previous assignments. But what is new is you're programming this particular trace to change color depending upon the value of the variable. Now, why is this important? Because just looking at the trace, you don't look. You need to look at indicators, or you don't need to find out the exact value of the variable. Just if you have a close look at this particular trace, by looking at the color, you can immediately see that this particular variable is off the normal range. Something is wrong with this variable, needs to be looked into. So this is a standard practice that whenever any variable crosses the normal limits of operation, the color of the variable or the color of the plot is changed just to highlight that something is wrong. Again, if I get back below 80, so it gets to green. Now, if I take it to below 20 on the lower side, you'll see something similar happening. 23. I've taken it to 19. You can again see at this particular point of time, it's gone below the normal range. So this changeover transition from green to red again highlights the fact that something is wrong with your level information, right? So this is one thing. Now the question is, how do I do this? Just go into the properties of level. Properties of the trace. We've done this before. So the only thing that I need to tell you is how to change color depending upon conditions. All this, how to define accesses, how to define variables. So this is, I just have one trace because I'm just plotting that manual value, which is supposed to be level, right? So you could have multiple traces. For each trace, you can define the color animation. It is there right at the bottom. This, you left it at the default values and all your assignments that you did before. So I can read it out. Probably it's too small for you to see. There's two options at the bottom. For each trace, just click the trace. And this is, of course, what is the color of that particular trace, what is the thickness and all that. You've done that before. But what is new is, the first is activate minimum warning. And there's a second option, activate maximum warning. Right? So if the value of the variable goes below a minimum value or goes above a maximum value, you can activate a warning. And what is a warning? A warning is basically a change of color. So next it is asking for, when you're activating a minimum warning, what is the critical lower value and what is the associated color when the variable goes below the lower value. Similarly, what's the maximum value and what is the associated color when it moves above the maximum value. So this is just the addition which helps you to highlight the fact that particular trace, particular variable is beyond normal values. So in our case, we'll be using this to highlight the fact that the level of liquid in the upper tank is either too high or too low, which is something abnormal. Right? You can also, of course, extend this. If the motor overload state is normal, you have one color. If the motor overload state is true, that is, you have an X color, you have a different color, and so on. So you could do it for all variables, but then this is just an example for one variable. Now, on the left, the next part is this. This is a digital indicator, nothing new. Many of you have already used this in some of your previous assignments. Again, what is different here is, again, color animation. We're trying to do the same thing that if you must have noted in the speedometers in all kinds of vehicles, whether it's a car, whether it's a motorcycle, you note that in between, there's a range which is marked green. Typically, say speeds around 30 to around 60, 70 or whatever is marked green. Low speeds below 20 or below 30 is marked yellow, and speeds above, say, 80 or 100, that's marked red. So you have a band which is optimum speeds, you have a band which is dangerously high speeds, you have a band which is unwantedly low speed, because if you drive at too low speeds, you're driving at a low gear which consumes large amount of fuel. So fuel efficiency drops. That is why very low speeds are normally not recommended. So we are trying to do something very similar. This particular indicator is displaying tank level. This is for the upper tank. You could also do it for the lower tank, but anyway, the concept is the same. Let's consider this is for the upper tank. I've linked this indicator to the same slider. You just saw the trace right now, which is linked to the slider. Someone trying to enter. It's the same thing. This indicator with a certain amount of color animation, again, the same concept. Say we say that any level below 20 is abnormal, any level above 80 is abnormal. Your level should optimally be between 20 to 80. And if your process is working fine, your level should be between 20 to 80. So if it's below 20 or it's below 80, above 80, something is wrong. That is what needs to be highlighted. So in order to draw the attention of the process operator, the plant operator, the factory operator, you're using color animation, because the minute he sees that this level has changed in color, he immediately knows something is wrong here. It's either too high or too low. Something corrective needs to be done. So how do you add color animation? That is the only point that I want to say, because the rest of it you already know. So again, go to the properties of this particular indicator. So you know there's something called a bar. So there you can define how the bar looks like, whether the scale is on the top of the bar, the scale is on the side of the bar. You do not want a scale and all that. So you can also define a scale. That is again understood. What is a scale? In our case, it's levels percentage, so it's 0 to 100%. So nothing new there. The only thing that I was trying to say was color animation. So obviously color animation is expected in this option that is called colors. So expand that. First, it asks you for a graph color. That is the default color of the bar. So I've said green, it could be anything. But normally we use green to indicate that some variable is normal within expected values. So that is why the normal color of the bar is green. You get down, at the end, there is an option called color range markers. Normally, it is set to no markers. That is a default value. And that is the way it was until the previous class. This color range markers, you can guess from the name, color range markers. That is, depending upon the range, you're changing the color. So color range markers, by default, this option is off. Here, I have enabled this. And once you enable it, then they ask for something called color areas. And of course, the names are not very standard names. I'm expanding color areas. Here you could find I've just named two areas. One area, I say the beginning of the area is 0, the end of the area is 20. Remember, my scale was 0 to 100. The size of the bar, minimum is 0, maximum is 100. Now the region from 0 to 20, I say that the color is red. And again, I say that the range for a region from 80 to 100 is again colored red, of course. That is abnormal. Whatever color you want to give, you can give. So the range of 0 to 20 has been assigned a different color. The range of 80 to 100 has been assigned a different color. So between 20 to 80, you haven't assigned any special color. So what it does, it takes up the default color, which is green. Initially, you had said that the color of the bar is green. So that's the default color. Now you're overriding the default condition. If you see, you're saying that if the value is somewhere between 0 to 20, you're saying that the color of the bar should be this. And similarly, I'm saying that if it's between 80 to 100, the color should be this. So you get the point that I can actually have multiple colors. So say 80 to 90 is okay. It's an alarm condition, but not a very serious alarm. It could be yellow. 90 to 100 could be red, and so on. Again, 20 to 10 could be yellow, and 10 to 0 could be red, whatever. But you get the point that you can actually change the color of this bar graph depending upon the value of the variable. So that is what has been done. If I just run this. Level is at 19. I said my minimum value is expected to be 20. See the plot, trace is red in color, and also the bar, which shows the amount of water you have in the overhead tank, that's again red in color. So if I take it above 20, 24 now, see the portion above 20 gets green. Of course, in coaches, this is not supported, but in certain other softwares, what you could do is you could change the entire bar to green. That is, as long as the bar is below 20, it's red. The minute it crosses to a value that is greater than 20, it remains green until you get to 80. But here what happens is, up to 20, that part is red, the normal part. So the minute you see that the top of the bar is green, what it indicates is fine, your level is within acceptable ranges until it gets to 80, which is my upper limit, because that's the way I've defined it. Get to a level above 80, see your trace changes in color, plus your bar also changes in color. So the minute the operator says that sees that this particular trace is red, or probably this particular bar is red in color, he knows that there's something abnormal in this particular level. Actually, you'd say that I already have a trace. I can see this in the trace, and why should I color my bar? I can see in the bar, why should I color my trace? Actually, I've put everything within the same page. But in practice, what happens is you have lots of information. You don't have one or two variables in a PLC. The number of variables that I handle is in the range of hundreds to thousands. So what they do is they have multiple pages for this particular display. So the bar graph is probably on one page and this trend is on a completely different page. So you don't have these two on side by side. So if you have color animation in the trend and if you have color animation on the bar graph as well, so no matter whether you're on the bar graph page or whether in the trend page, you immediately get to know that something is wrong with the value of this particular variable. Here, of course, the information seems to be redundant. I've said the same thing both in the bar graph and in the trace. Probably it appears that why should I say the same thing twice? But the reason is that in practice, okay, in one page you simply have such bar graphs indicating levels in multiple times, and trend page is a completely different page where you just have a huge plot showing multiple variables, huge number of variables. As a matter of fact, you could have multiple trend pages because you have a huge number of variables. So when you can normally see trends, you don't see the bar graphs. When you see bar graphs, you don't see trends because multiple pages have been used in the HMI or in the visualization. So that is why you use color animation in both places. It's not actually redundant. Now coming to the third part, alarms. Now alarm is something very important in any process plant. It is extremely important in any factory. What's an alarm? It simply highlights the fact that something is abnormal in your process, something is abnormal in your machine. The operator is informed, the operator is intimated, the operator is told that something is not right in the process, something is not fine with the machine. So it needs your attention. You need to set it right. You need to correct whatever fault has occurred in the machine, whatever fault has occurred in the process. You have it in the mobiles. What does a mobile do? It continuously monitors the charge level of your battery. So if the battery charge level is low, what is low? That is, of course, a different issue. It could be 20%, it could be 10%. You immediately have a notification which says that the charge level of your battery is low. So you need to take corrective actions, which means you need to recharge it. So it's something similar there. It's just one variable that is being monitored, the charge level of your battery. Or even if your signal strength becomes very poor, what we normally call towers. So you have a very poor signal strength, almost no towers. So immediately you get a cross there where the towers are shown, and it tells you that the signal strength is too poor, and that is why the phone is not able to communicate. So these are very crude examples of alarms in our day-to-day lives. But when you go to a factory, when you go to a process plant, the number of variables that are monitored is huge, and this alarms is a very important part because you need to continuously monitor the process. Monitor means check whether each variable is within normal operating range. If any variable goes outside the normal operating values, indicating something is abnormal within the process, within the machine, it's got to be highlighted. The operator has got to be told that something is wrong and you need to correct it. You need to take corrective actions. As I said in the this one, in the controller that PD discussed, you had to, the responsibility of developing the alarms was yours. You wrote the software or you will write the software to develop those particular alarms. No, the alarms were, one was that there was no water in the sump. The second alarm was overload condition is true, and the third alarm was that the tank did not fill up with a certain amount of time. You had a acknowledge button, that is whenever alarm comes, the machine generates the alarm, but then the machine needs to know whether the operator has actually seen the alarm. So there's an acknowledge button. Whenever that particular acknowledge button is pressed, what it means is that the operator has seen that particular alarm and he possibly is taking corrective actions. And the standard practice is all alarms are logged, just like the trend is stored within a server, within a historical trend server, it's stored within the hard disk. All alarms that are generated and all alarms when rectified, this information is stored within the hard disk. So that again, if you have a fault, you can find out what was the actual reason of the fault, what alarms occurred, whether they were attended to or not, whether they rectified or not, why does this particular fault occur. So all kinds of alarms are by default logged. Logged means that information is saved within the hard disk. Now the question is, how do you generate alarms? As I said, Alarm generation. The responsibility of alarm generation is not on the user. You don't need to write programs for that. That functionality or that feature is built into this particular software. It's built into CodeSys or any other similar software. You just need to define the alarms that you're interested in. You need to simply configure that, right? So this is a different project. What I've done is I've just defined 3 variables which are linked with our tank example so that it's easier to understand. I have a level data. Again, I'm just generating the level manually. I just have a slider. If this one change the position of the slider and assume that the level changes. I have an overload sensor, just like you have on your motor. The overload conditions could be true or false. As you know that you need to generate an alarm whenever the overload condition is true. And third is you could have additional alarms, one for say whether there's sufficient water in the lower tank. But then I've not done that because the logic is the same. If you know how to do it for one variable or 2 variables, you can do it for any number of variables. It's just a matter of time. So I've defined 3 variables. One is level, which is an analog variable, as you understand. It can change from 0 to 100%. So the data type is integer, the variable is level. You have another overload, which is a Boolean variable because it is either true or false. You have a sensor, which is built into your motor. It monitors a motor current. So the motor current is within the normal range. Overload condition is false. And if the motor current is greater than the normal operating current, you have an overload condition and the output is activated. So the output of the overload sensor is a Boolean variable. It's just true or false, right? So you have an overload variable of type Boolean. Overload true means you have an overload condition, generate an alarm. Overload false means you do not have an overload condition, do not generate an alarm. And third, I have another Boolean variable called audio alarm. As you have done in that particular previous assignment, version 1, if you have done it, you know that in addition to visual alarms, you also require an audio alarm. The reason is it may so happen that the operator is not right in the front of the screen, or even if he's in the front of the screen, he's probably got distracted by something else, not looking at the screen. So what you have is you have an audio output whenever an alarm condition occurs. It is meant to draw the attention of the operator towards the screen. Okay, it's a common alarm. Any alarm, when it is activated, results in the audio output being generated, right? For example, you have this alarms in your mobile phone. You want to wake up in the morning, so you set an alarm. Okay, something comes up on your screen, but obviously there's an audio output, because if you don't have an audio output, just providing you a visual output on the screen of your alarm will not wake you up. And something very similar. The audio output is primarily meant to draw the attention of the operator to the screen, and then looking at the screen, he has complete information as to why the alarm was generated, which variable is abnormal, what is the value of that variable, and so on. So you have another variable, Boolean variable called audio alarm. This is activated whenever any alarm condition occurs, and this is deactivated whenever it is acknowledged. Acknowledged, remember, I told you that the machine generates an alarm, your system or CodeSys generates an alarm. Now CodeSys needs to know whether the operator actually has seen this alarm. So what does it do? It has a button called acknowledge. So the operator notices this alarm, he comes and presses this acknowledge button. What happens is CodeSys now gets to know that this particular alarm has been noted by the operator because he has pressed the acknowledge button, and so the audio output goes off. And even you can have some changes in the visual output. We'll get to that, because in the previous assignment, what you did was, if I remember right, initially that lamp was flashing whenever alarm came in. There was an audio output. You acknowledged it. What happened was the audio output went off. The flashing light became steady. It was steady as long as the alarm condition existed. When the alarm condition went off, it became normal. I guess that is what you did in that assignment. So you can define all such situations within this particular package, which is called alarm configuration. So how do you add an alarm configuration? I've already added it. What you need to do is application, which is on the top. Right click on application. As before, add object. You are added POU, that is, whenever you add a function block or whatever, you add a program, you added POUs. Now, instead of adding a POU, you add visualizations exactly this way. Now you're not adding a POU, you're not adding a visualization. What you're adding is Okay, I need to remove the alarm configuration because I've already got an alarm. Right? Application, add object. The very first item, because it starts with A, is called alarm configuration. That is, you're trying to configure, as I said, all the software for generating alarms is built into it. You just need to say that what are the alarms that you are interested in and what is a condition that generates alarm. Right? So that is what you specify in so-called alarm configuration. Click alarm configuration. It comes with some default name, alarm configuration. If you want to change it, you can change it. Otherwise, you can go in for the default name. Okay, I go for the default name. So it's added alarm configuration. Additionally, it's added some 3 or 4 entries under alarm configuration. What they call it is error, info, warning, or whatever. And alarm storage. That is what is the amount of space that you want to allocate for storage of the alarms, how much MB or whatever. But let's also leave it to the default values. Okay. Now, in alarm configuration, you are basically wanting to define alarm that is associated with your application. In this case, in the case of this tank, the alarms are basically say overload, no water in the sump, and third, I'll add that too high a level in the overhead tank or too low a level in the overhead tank is also an alarm condition. So what you do is right click on alarm configuration. What do you do? What I want to do is add objects. Right click on alarm configuration, go to the option which says add object. And what do? What object do you add? I add something called alarm groups. So it says create an alarm group. That means it's a group of alarms. Normally what you do is when you have a large plant, when you have a large machinery within a particular factory, you normally group alarms related for one machine. All alarms relating to one machine is group 1. All alarms relating to second machine is group 2. And so that you logically normally associate alarms with a particular machine or with a particular part of the process. Right? So if you have multiple this one process as you normally have in a large factory or large process plant, what you normally do is you classify or you group alarms linked with one part of the process, one machine within one group. So here you could give it any name. It's called alarm groups. So here this is tank alarms because this is related to my tank filling system or whatever you call it, tank filling system or tank alarms. So you have, blank is not allowed in between. So tank underscore alarms. So what you have done is you have created a new group of alarms, which you call tank alarms, because in this case, all these alarms are linked with, associated with this tank filling system, right? Okay, we are in tank alarms group. Now you got to define what are the alarms that you're interested in, right? You got to tell the system. It has a software for generating alarms, but it doesn't know what alarms you are interested in. It doesn't know the alarms that are important in your system. So that is what you need to do here, configure. So that is why this is called alarm configuration. Unfortunately, German software, so all English is very peculiar. The first is they call say something called observation type. What it means is this is where you need to define all the alarms that you're interested in. Observation type, if you expand this, the first, I guess you can't read it, the first option comes out to be digital. So what this means is you are associating an alarm with a Boolean variable or with a two-state variable. For example, say overload sensor. The output of the overload sensor is a Boolean variable. It can have only 2 states, true or false. Now, one of them is a normal state. The other one is a abnormal state where you want to generate an alarm. So if you want to associate an alarm with one of the states of a Boolean variable, then it's called a digital alarm. Digital alarm means the variable with which you are trying to associate an alarm is just a Boolean variable. It has 2 states. One of the states is a normal state. The other is an abnormal state. You want to highlight that by generating an alarm. In our case, Overload is an example of a digital alarm because the overload sensor has only two states. Insufficient water in the lower tank in the sump is a Boolean alarm because there what you have is just a level sensor, a level switch. It generates two states. One, if there is sufficient water. Second, if there is insufficient water. So if there is insufficient water, you want to generate an alarm. Again, that would be an example of a Boolean alarm because this alarm is associated with a level with the sump level, which is a Boolean variable. It has only two states: sump level sufficient, sump level insufficient. So sump level sufficient is a normal state. Sump level insufficient, that is you don't have enough water in the lower tank, that's an abnormal state, generate an alarm. So one is digital alarm, fine. In this case, I just have one variable, that is overload. You said that my first type of alarm that I want to use in this particular system is a digital alarm. Okay, details. When I click the details, okay, all you said is you have a digital alarm. Now what do you need to say? You need to say what is the variable, with which variable are you associating this alarm, and when does the alarm occur, when the variable is 0 or when the variable is 1. So here at the bottom, corresponding to the digital alarm, you have something called an expression. The expression is, in my case, is just one of the variables which is called overload. So in your case, it would be overload, it would be some level, low or high, whatever, and it would be tank level low, tank level high. Tank level, in this case, I'm talking about the upper tank level. So you have selected that variable, it's called overload, which is alarm condition. Overload 1, overload is true means an overload condition is occurred. So that is the abnormal condition. So here you write this variable equal to 1. So that has come here. This particular variable PLC underscore program, that is the main program, dot overload, that is a variable equal to 1 is the alarm condition. Okay. Deactivation, forget it, leave it at default. Next, you need to specify the message that whenever this alarm condition occurs, what the system does is it puts up a message on the screen. It says overload of this motor. Normally what you have is probably tens of motors, hundreds of motors, or even thousands of motors in a large plant. If you just say that overload has occurred, it is meaningless because you do not know this overload is linked with which motor. So you got to say a motor number this, or more meaningfully, motor associated in this part of the process has an overload condition. So just the text, whatever text you write over here, all it does is it stores that particular text and puts it up on the display whenever you have an overload condition. So I'll simply write motor overload. I just written the motor overload. Now there's another thing that you need to select, class. Class means alarm class. By default, generates 3 classes. It's marked error, info, warning. So now what's in a class? What do you define in a class? I'll come to that. By default, I'm just selecting error normally. Actually, the details of the class you define. Now what exactly is in a class? I'll come to that. So I've defined, all I've said is I have a digital type of alarm. And what is the alarm associated with? It's associated with overload. When does alarm, which is alarm condition? The alarm condition is if overload is true. Now, when this overload condition occurs, when this alarm condition occurs, what is displayed? The message that is displayed is motor overload, and it's associated with some kind of a class called error class. Okay. I'll define just another, this one alarm. I've already finished defining my first alarm. The second alarm say I want to generate an alarm when the tank level is high or the tank level is low or both. Say we want to generate an alarm when the tank level is above 80%. We've already done that. The color was changing from green to red. So after digital, the next option, I guess you can't read it, says upper limit. The third option says lower limit. Fourth option says outside range. Fifth option says inside range. Sixth option says change or rate of change. Now, what does all this mean? Upper limit means here the variable is not a digital variable. Here the variable is an analog variable. Typical example level, because it's changing from 0 to 100. So here you got to define an upper limit. So if the variable crosses the upper limit, you have an alarm condition. Lower limit means if the variable goes below a lower limit. What is the lower limit that you got to define? Then you have an alarm condition. Outside range means you got to define a band. Within that particular band, if the variable is within that particular band, it is normal. If it goes beyond that particular band on the upper side or the lower side, it's an alarm condition. It is inside range is again just the opposite. Rate of change, that is the rate at which a variable is changing. If a variable all of a sudden, again, all this is meant for analog variables. For example, if you have a tank, the level cannot change very fast because the rate at which you can fill the tank or the rate at which you can move water outside the tank is restricted, is limited. So all of a sudden you see that the level has abruptly changed. That means something is wrong. So you could associate an alarm with the rate of change of a variable. Normally a variable should not change very fast, depends upon the nature of the variable. So if there's an abrupt change in any variable, it signifies that something is wrong somewhere. So you can associate an alarm condition with the rate of change of variable. So all the software, how to generate the alarm is built in. You just need to say what kind of alarm you're interested in. In this case, say we are generating an upper limit alarm. Upper limit alarm means this is associated with an analog variable, fine. So I've clicked upper limit. What it says is expression. What is the, it could, expression means it could be a variable, it could be a mathematical expression. So my case, it's very simple. I'm trying to associate this with level. So I have level, associate that with level. And when is this alarm generated? When this particular level is greater than, you have an option here, greater than or greater than equal to whatever value. In our case, this is simply 80. So it means that when this particular variable is greater than 80, this alarm is generated. You could also define a hysteresis. Hysteresis means, for example, it is 80. Now say if the variable is 80, you have an alarm condition. If the variable is 79.9, you don't have an alarm condition. Now this could be problematic. Why? Because the level of liquid in a tank normally has turbulence. Turbulence, Bangla means dheu khala. Whenever you're filling liquid or you're moving something within a tank, what happens is there is turbulence on the surface of the liquid. That is a liquid, this one level moves up and down. Just the way when you throw a stone into a pond, the surface of the liquid is not stationary. It moves up and down. There are waves or there are ripples, whatever you call it. So whenever there's turbulence, what is happening is the level of the liquid is moving up and down. So there's variation in level about a mean value. So if you do not have any hysteresis, what would happen is this variable or the level alarm state would be continuously changing, because you said 80 is an alarm state, 79.9 is a normal state. So the level is fluctuating about a mean value. You continuously have alarm state, normal state, alarm state, normal state, which does not give any useful information or picture. So you got to damp out such undesired variations. I mean, this is exactly why you use hysteresis in a voltage comparator. You use positive feedback, introduce hysteresis. Why? Because the input voltage, there could be small fluctuations because of noise. If you don't have hysteresis, then the output state will continuously toggle when the input voltage becomes equal to the reference voltage. Something very similar. Of course, it's your choice. If you don't want hysteresis, put hysteresis to 0. If you want hysteresis, you can define the percentage hysteresis. That's your choice. I'm leaving it at 0. So you have defined a second alarm. It's called an upper limit alarm. That means whenever this variable gets to a value greater than 80 or whatever you have defined, you have an upper limit alarm. Okay, so this way you can keep defining alarms. I go back to my previous state, which is already worked out. That was alarm configuration. This is alarm display. Where do you get alarm display from? Okay, I forgot showing that. It's right here. You go to the visualization screen, visualization toolbox. Somehow my visualization toolbox seems to have disappeared. Where has it gone? Toolbox, there, nothing is there. Anyway. No idea why that has disappeared in that particular project. I'll show you where the visualization toolbox is. Sorry, where this alarm. This is that visualization toolbox. As you know, you have basic, common alarm, this one common controls. Then you have something called an alarm manager. In alarm manager, you have just two entries. The very first entry is an alarm table. That is how the alarm is displayed. So long, what we looked at was alarm configuration, how you define alarms. So ultimately, when the alarms are generated, it's got to be displayed, right? So that operator can have a look at that. So it's a part of your HMI screen. It's a part of your visualization screen. So what you do is just take this alarm table and drag it into your visualization screen. So that is what I've done. So this is my alarm screen. Okay, for the time being, I have just two variables. I'm running a demo. One is level. Remember, in this, what I've done is I've defined two alarms. One is greater than 80 is a high alarm. Less than 20 is a low alarm. And I've also got this one, a push button, which so-called indicates a sump level. So I've labeled the sump level okay. So if this is 1, that means that you have enough water in the lower tank. So sump level is okay. If this is 0, then you do not have enough water in the sump. So that again is an alarm condition. So basically here are 3 alarms. One digital alarm that is associated with sump level. If it's 1, it's normal. If it's 0, you have an alarm condition. And I have one upper limit alarm and one lower limit alarm, both of which is linked with the level of the liquid in the upper tank. These are the 3 alarms, right? So initially, let's start off with sump level. Now sump level is 1, so it's a normal operating condition. Now, if there is insufficient water in the lower tank, then sump level becomes 0, turn it off. Immediately, you have a red bar. What you cannot read is probably there are 2 things in this particular table. First is timestamp. So you have a printout of the real time as well as date when this particular alarm occurred, and you have a message. This message was just the message that I was a little while before entering. Here it says sump level low. It says sump level low because that is the message that I've entered. You can enter any message, and when this alarm condition occurs, that message is put up over here. And this bell shows that you now have an audio output. Of course, I don't have an audio output. This is a representation of the fact that you've got an audio output because you have got an alarm condition. Now, at the bottom, there are 2 acknowledge buttons. One is acknowledge selected. One is acknowledge all visible. That means you could have multiple alarms. For example, say sump level is low and my water level goes below 20. Now see, you have 2 alarms. One of the alarm reads level is low. That is on the top because that came in later. And the lower one says sump level low. Both of them are red because both these alarm conditions are presently true. Presently, the level is below 20, so sump level is low, so the tank level is low. And presently, this particular push button is off, which also says that the sump level is low, insufficient water in the lower tank. So now I could acknowledge both these alarms individually. Then I use this first switch, alarm selected, or I could acknowledge all the active alarms in one go. Then I use this. For example, now I press acknowledge all alarms. That is, you have 2 alarms. I press this. See, the color changes to light red. I mean, this you can define. What it means is both the alarm conditions are still present. You have just acknowledged it. So the first condition was an alarm came in. Alarm means abnormal condition. Second condition is you have acknowledged, but the alarm still exists. because now still the level is below 20. That's an alarm condition. And the sump level is still 0. That's also an alarm condition. Now, what happens if this alarm condition goes away? You get back to a normal condition. Let's press the switch. Now, sump level OK is 1. That means you have enough water in the lower tank. Say instead of 2 alarms, 1 alarm is visible, which says level low, because you have low water in the overhead tank. But the other alarm has disappeared because the sump level is now back to normal. If you take this level to a value greater than 20, the second alarm has also disappeared because now none of the alarm condition exists. You have enough water in the sump. You have water greater than 20% in the overhead tank. Now let's do a second thing. Again, say no water in the lower tank. So you can see there's an audio output and this is marked red. That means this alarm has arrived and still there's insufficient water in the lower tank. Now say I have not acknowledged it. The operator is having tea or coffee or somewhere, is not in the control room. He doesn't note this alarm in spite of the fact that you have an audio output, or probably he has gone to brigade. This is election time. So he's attending some campaign or whatever. So he has no time to acknowledge this particular alarm. So what happened is the alarm condition has occurred and it has not been acknowledged. So someone takes a corrective action, not the operator. Someone else has taken a corrective action. And after a certain amount of time, he has added water to the lower tank. So the sump level returns back to normal. See, now what has happened is now the color, instead of being light red, has changed to yellow. What this means is you had an alarm condition. The alarm condition has been rectified, but you've not acknowledged it. So this yellow means that the alarm condition, an alarm had come in, then alarm condition got corrected, it got rectified, the alarm condition no longer exists, but the operator has not acknowledged it. So still the audio alarm or the audio output is active. Now, if this is acknowledged, the audio output disappears or stops and the alarm disappears. So why it disappears? Because it's already been rectified before you could acknowledge it, right? So that is a second situation. So the first thing is an alarm condition occurs. Normally what should happen is after an alarm condition occurs, you should acknowledge it. So the second state normally is you have acknowledged it, but the alarm condition still exists. Third condition is alarm condition gets rectified or corrected. So fourth condition is if the alarm condition gets rectified or corrected, the alarm display at this particular point disappears. So this, now here you had, see, this comes in red. If you acknowledge it, this has turned into something light red. It's disappeared. It's become normal. It turns yellow. Now all these colors, that red or yellow or whatever, light red, or this particular text, the font, all that is defined as what is known as alarm class. If you are seeing this, what we have seen, that 3 classes were generated. If I just open one of the classes, so this is called error class. Priority is the importance of the alarm. 0 is the highest priority, and I think the maximum value supported is 30 or whatever. So as the number increases, the priority actually comes down. It's the other way around, right? Now, the mode of acknowledgement. There are 2 or 3 different modes of acknowledgement. What we have done is something called REP acknowledge. This is something very specific to coaches. It's not a standard thing. But what it means is whenever you have an alarm condition, first of all, the display comes, then you have got to acknowledge it. If you acknowledge it and the alarm condition exists, there's a second state. And when the alarm condition goes off, the alarm display disappears. That is what is this particular acknowledgement state. And below you can define all these colors. That what is the color when the alarm comes? What is the color when the alarm is being acknowledged? What is the color when the alarm has come and disappeared but not acknowledged? All this is disappeared in this, but all this is defined in this particular table. So this lower table normally says that particular color codes corresponding to alarm appearing, corresponding to alarm being acknowledged, corresponding to alarm getting back to normal. All those color codes are defined here. That's your choice. plus the kind of text, I mean the font, whether it's bold and all that is defined within this particular table. So that is what is alarm class. You basically define what kind of acknowledgement you're interested in and what kind of color code you're basically interested in to represent different states. So that is what is, they have already built in 3 classes. Error, info, warning. You can build your own class if you're interested, but any one of the classes should be more than sufficient. So what I've done is I've just included, whenever you define an alarm, what I missed out was here you've got an entry called class. This has got to be filled in. You can't omit this. There's no standard option. So just enter the standard error, info, or warning, anyone that you're interested in as one of the classes. These classes are already built in this particular system. So that is what is an alarm class. So that is how alarms are generated. If I just acknowledge it, acknowledge selected. Yeah, the alarm is gone because you have enough water. So, and equally important is you got to remember this alarm data is always logged. Logged means it's stored in the hard disk. So that you can later retrieve and find out when did the alarm occur, when was it rectified, when was it acknowledged. Actually, you can get hold of the operator whether he was doing his duty the right way, because whenever an alarm occurs, he's supposed to acknowledge, he's supposed to take corrective actions so that the alarm condition gets back to normal. So you can just view the log. When did the alarm occur? When did the operator acknowledge it? When did he correct this alarm situation? When did he rectify it? When did he get the situation back to normal? So all that is present in the alarm log, and you can get hold of the operator as if he's not doing his job right. So this entire logic of how the alarm is generated, it's not your responsibility. It's part built into this particular package, Coatsys or any other similar package. You just have to configure the alarms. You just got to say what are the alarms you're interested in and what are the values when the alarms are generated, type of alarms, digital alarm, analog alarm means upper limit, lower limit within a particular band, rate of change. All that can be defined. What are the color codes you're interested in? What is the text message you want to display? So you just say all those things and the alarm generation is automatically done by the software. Okay, so if anyone wants to display anything, I mean, they give a demo, you can stay back, and others just send in your the roll numbers on the chat box, and you can sign out.
Hello, sir.
Yeah.
Sir, আমি আজকে ডেমো দেখাতে চাই, আমি একটাও দেখাইনি সেজন্য। ঠিক আছে স্যার।
আর সবাই অ্যাটেন্ডেন্সটা দিয়ে দিও, তোমাদের এখানে ওই নাম আর রোল নাম্বারটা লিখে দিও।